Hello, this is Pat Hindle, Microwave Journal Editor. Welcome to today's EDICON online session, The Journey to LTCC Components for mmWave Applications, presented by Aaron Vaisman, LTCC Product Line Manager at MiniCircuits. For more information on our speaker, please see the biography box in the lower left-hand of your screen. Today's 5G IT track is sponsored by National Instruments and ThinkRF, and this workshop is sponsored by MiniCircuits. Before we begin, let me introduce you to today's platform. In the center of the screen, you will see a window containing the presentation. You can enlarge this to full screen. The window labeled Resource List contains a copy of the presentation and other available resources for this talk. This session will be available on demand later so that you can watch it again and recommend it to colleagues. You can also use the paper airplane icon at the bottom of your screen to share it immediately with friends and colleagues. If you have technical problems, please click on the yellow box with the question mark at the bottom of your screen. After the presentation, we plan to have time for questions. If you have a question, type it into the Q&A box on your screen at any time. Now I will turn this session over to Aaron.
Pat, thank you very much for your introduction and welcome all to this presentation. The LTCC technology is nowadays considered a mature technology. For instance, MiniCircuits has been supplying products for more than 20 years. We have currently in our catalog 700 plus components within our LTCC offerings, and among those you can find filters, balloons/transformers, couplers, power splitters, BISTs, limiters, mixers, amplifiers, among others. Those products cater more than 20,000 customers around the globe. So we have really been in the market for a long time, proving that the LTCC is really a viable technology for any application below, I would say, between 10 to 13 gigahertz. It's a very flexible technology to work with. It allows for implementations on the low volume ranges to high volume ranges. It is a mature technology. It allows for a vertical stacking of many layers, so it reduces significantly the footprint that a component uses within a system's motherboard. The high permittivity of the material, the intrinsic materials used on this technology allow for a high miniaturization rate of any circuitry that we embed within the actual LTCC. And thus, LTCCs have been predominantly a technology being employed for lump component implementations, mainly filters made out of L's and C's, stacked throughout many, many layers, as much as 30 layers, for instance. This technology is a self-packaged technology. It's a monolithic structure, and because of that, it can be easily translated from a tape and reel onto a board on a pick-and-place process. And MiniCircuits has been on this business of supplying high-performance LTCCs for more than 22 years. Up until now, there hasn't been a need for cost-effective circuit structures in the higher frequency bands. Applications such as radars, some collision avoidance radars, for instance, and up to an extent, some satellite communications have been operating above 10, 13 gigahertz. But these are not truly considered cost-sensitive commercialized applications. Now, there is a need for cost-effective circuit structures at those frequencies. This is mainly due to the proliferation of 5G standards and the vision on advanced generations of Wi-Fi, which are targeting operations in the mmWave range. The question that we have at MiniCircuits is LTCC a viable solution path for it? Do we really have a technology that is capable to implement circuitry and perform all the way up to the millimeter waves, we know for sure there are some needs. We know that there are new needs for lower cost structures at higher frequencies. We know that there are requirements that until now the higher frequency applications have not required high volumes, for instance, nor cost-effective solutions. And we see on the LTCC, knowing what we know about the technology, that there's a need for cost-effective circuitry that could be supplied by components such as LTCCs, and that could well cater the applications such as 5G and Wi-Fi coming up. But we are uncertain if the LTCC is actually the right vehicle to implement circuitry at those frequencies. And the doubts come out of common knowledge. The industry knows that the LTCC has constraints. And those constraints are not limited to the mini-circuits brand. They are related to the actual technology, the actual process that makes this technology, the actual materials that compose this technology. And for instance, we see that this technology, it has constraints, limitations. 20 years of experience with this technology credit us at mini-circuits with the understanding of these limitations related to the technology. And the most relevant will be the following. This technology is implemented mainly as a thick film process. The line width definitions are subject to such a process where the conductors are deposited through a screen printing process, and there are tolerances on the line widths, and there's a shape to the line widths that is not uniform across the line width itself. There is a poor definition of the corners of bends, for instance, or as a matter of fact, of any intersection between two traces, as you can well see in this left picture that I have placed here. Moving from left to right within our pictures, I'll show you another limitation. This is a cross-section of an actual conductor embedded within an LTCC. And you can see how, from left to right, this conductor changes height. Its profile changes. And this is mainly due to the deposition of this thick film, of this thick paste through a screen printing process. The technology has also limitations in regards to layer-to-layer registration. Remember, we're trying to stock up here many layers, as much as 30 layers, for instance. And we need to align them pretty well. But there are tolerances on that alignment process. There's also shrinkage factors that need to be considered. These conductive pastes are deposited on top of these LTCC substrates on what we call a green sheet state, which is a pre-fired version of the LTCC. So we screen print those conductors on top of these layers, and then we stack them up as much as we can, and then we fire the whole thing together, creating a monolithic structure. Well, within that firing process, it's very well known that there are shrinkage factors that play a major role to the end dimension of the component. And we have to scale our printed version of our conductors in such a way that compensates the shrinkage factors. And the complication comes when we realize that those shrinkage factors are not set in stone for a given material system, for a given LTCC material system, to be more specific. They highly depend, for instance, on things like metal loadings and the actual design per se. So we need to really experiment on a design basis with the actual process. This is a major complication on the implementation of circuitry within this technology. And last but not least important, we see that the conductive paste being deposited within the LTCC need to be co-fireable with the actual ceramic material at very high temperatures. How high? About 900 degrees Celsius. And the challenge is not only to fire the conductive pastes along with the tape layers, with the ceramic material, but to have a reliable bond between the actual ceramic material and the conductive paste. And in order to achieve that, we need to embed some glass content within the actual conductive paste in order for that glass to diffuse into the ceramic while the sintering process takes place, and thus ensure a good adhesion of the conductive traces to the actual LTCC. But that glass content, as you can imagine, embedded within a conductive, it only brings losses. So therefore, the LTCC has been seen as a lossy technology for a long time, suitable to just certain types of applications where performance is not the most important subject. So we know we have constraints. We know the constraints are related to lossy materials. LTCC conventionally viewed as a lossy technology relative to our materials. We also discussed problems with line width definitions and tolerances to that end. And we know that we're aiming towards implementations at mmWaves, where dimensions become more and more critical. Tolerances will become more and more relevant. Line widths and tolerances on the same play a major role whenever we're trying to implement circuitry at those frequencies. And yet, we have also a major problem, which is due to the high integration within a monolithic structure on a very constrained volume, parasitics are abundant. We have tons of them. Cross-couplings without intention, unintended capacitances between components, unintended capacitances to ground planes, proximity of ground planes to structures dequeuing the actual internal components, and so on and so forth, are major constraints within the actual technology. What are our options? Knowing the current limitations on what can be executed by the LTCC technology, what our options are available? We know there is so much that can be integrated on a chip. There's a world tendency, our industry tendency, to incorporate stuff within chips. But chips themselves, the semiconductor technology itself, has its own limitations. And we still see at Mini Circuits a need for supportive components around those chipsets. So we are asking ourselves, how about the components surrounding those semiconductors? I have listed in this table some of the available technologies that have been assisting somehow the operation and the applications of interest at higher frequencies. And among those, yes, of course, we have the LTCC. We're considering also a mimic technologies, more specifically gallium arsenide, because it is considered less lossy as compared to, for instance, silicon. Alumina has been a long player when it comes to the implementation of especially filters. Cavities, of course, for sure, with their own limitations. Some of you may have been implementing filters or attempting to implement structures on the PCB itself. And there's lump components, especially below 10 gigahertz, have been prevalent. So on both structures, same statement as lump components below 8 gigahertz probably have been really prevalent, especially on the handheld side of the equation. And some more folks like 3D Glass having good technological proposals, but all of them have constraints. And this heat map represents the flexibility, basically, of each one of these technologies whenever we try to categorize them among many, many attributes, such as the performance itself, the development speed, the development costs of each one of these technologies, the per unit cost that can be achieved on a production level, surface mountability, availability. For instance, we know for sure cavities cannot be surface mounted. They're bulky, big devices. Business feasibility on minimum order volumes, optimal frequencies of operation. So we see that some technologies offer a broader bandwidth offering when it comes to components being deployed to the market versus others. Sizes. Some technologies offer smaller or larger devices, and so on and so forth. You'll have this table available as soon as you download the slides. And without any bias, I assure you, we have taken the time to grade each one of these colors, where the green color has the highest grade. We have an intermediate grade for the yellow color, and the lowest grade will be provided to the red colored cells. And surprisingly, the highest grade, after you come up with that exercise, is attributed to the LTCCs. So the LTCCs demonstrate once again their flexibility. How flexible this technology is among our technologies, competing technologies within the applications of interest. So there are plenty of things out there, but they all have shortcomings. It is apparent that the LTCC technology continues to be a great complement to the highly integrated MMIC chipsets. Nevertheless, we're still left with a question on how to overcome the well-known constraints of the technology. So we at Mini Circuits, we believe that there's a hint for a future of components being implemented in LTCCs. So in addition to the other technological alternatives that we just discussed, the academia has been attempting to employ the LTCC as a mean to implement millimeter wave structures. Nevertheless, these developments up to date have yet failed. Well, they have failed in one end. I would say they have failed to prove the viability of the technology on a production scale. This is mainly because their implementations are just prototypes built on very, very, very small batches, far from the industrial needs, without yet demonstrating volume and price scalability to accompany the potential electrical performance, not to mention a thorough qualification process that takes care of the reliability aspects of these components. So, what are we doing to overcome the constraints, the provided constraints, the known constraints of this technology? Well, we started with the material. We started with the actual material science. We really needed to characterize in depth this material, the LTCC material system. As a matter of fact, we're employing more than one material system in our LTCC implementations. So we needed to characterize them all and find out what is the performance like, what are the electrical attributes and characteristics all the way up to the millimeter waves. So we found this material to be lossy, indeed, dispersive, meaning the permittivity changes over frequency, anisotropic, The permittivity changes with respect to the plane of incidence of the waveforms, of the EM electromagnetic power. Now, we do understand where the limitations are coming from and where do we need to focus our efforts to circumvent those limitations. And this was a very, very important step in the development of millimeter wave products with this technology. So we knew that if we had powders, smoother powders, with more uniform granular structures, lower loss tangents, and capable of being co-fired with higher conductivity pastes, which at the same time would have a better line width and thickness control, we would have a chance to produce components at much higher frequencies. So we started with engineering new powders that had finer granular structures, powders that will be less lossy. Then we work on smoother surfaces. We needed that those powders yielded smoother surfaces. Surface roughness, it's a very well-known parameter, performance parameter when it comes to losses. And people tend to think that the surface roughness is relevant only on the conductors. Well, in this case, it's not just the conductors that need to be smooth. It's also the surface where these conductors are being printed on top of it. There's a high-density field quantity at the interface of the conductive paste and the actual material and the actual LTCC. And due to that, we needed to improve the surface roughness of the actual LTCC. We also needed to work on conductive paste that they were more conductive, that they had a higher conductivity, for instance, meaning lower glass content. And with all these attributes, like smoother surfaces, more uniform granular structures, and higher conductivity conductive pastes, we were expecting at the time of the experimentations that we would be achieving more consistent, better fidelity, lower surface roughness implementations, yielding viable products for millimeter wave applications. So the combination of much smoother LTCC surfaces along with a fine line photoimageable screen printing process has enabled outstanding performance improvements at millimeter wave filter applications. And yes, I just introduced a new term, photoimageable screen printing process. Let me explain a little bit more what is this about. We at Mini Circuits, we developed a paste that it can be still screen printed onto an LTCC surface, but then we have a glass mask that will produce a photolithographic process in order to etch some of the conductive paste, remove it from the surface of the LTCC, like as a parallel to what we see on the PCB photolithographic process, and then we will be left out with much smoother, much more consistent, much well-defined conductive pastes. And we can see a striking parallel on these pictures that I'm showing here on this slide. Basically, you see on the right half of your slide, of this slide, a comparison between what is a screen printing process versus a photoimageable process. You can see the corner definitions, they're much better defined. You can also note that there's no longer this domed shape that we used to have on the traditional screen printing process. Rather, we have a uniform thickness of the conductive paste on the photoimaginable process. Look at the corner definitions again, and the tolerances on the line widths have been tremendously improved. And as an example to this development, to this technological development, we have been able now to improve what I have here as an example of a filter, a bandpass filter, which has been implemented with both types of technologies, meaning the blue trace representing the standard LTCC technology up to date, which is based on a screen printing process, and an LTCC powder and material system, which is a standard material system, versus what we see in red as the implementation of the same exact circuit, but now translated onto a cutting-edge LTCC technology with photoimaginable traces, as well as an improved material system, powder system, much finer grain structures, and so on and so forth. And the differences in the passband insertion loss, midband insertion losses, are striking. We're looking at more than 1.5, almost 2 dB improvements on the passband frequency, and we're looking at measured data of a device which is centered at 28.5 gigahertz. That is once a new set of material systems, conductive paste, and brand new fine line printing processes were developed, it opened the door to explore the possibility of implementing circuital topologies much more aligned with transmission line approaches rather than lump component realizations. These new breed of wavelength-dependent implementations led to the fabrication of components based on edge and broadside couple filtering structures, substrate integrated waveguides, yielding low in-band insertion losses, low emissions, high isolations, brand new package realizations including strip-line launches, much deeper and broader stop-band rejections. And last but not least important, sustained performance at frequencies beyond the X-band. So I'm going to surf through slides here, just showcasing some of the developments that we've done here at Minute Circuits, and that they will be hitting the market very, very soon. So we have here an example of a substrate waveguide implementation. This is a filter at 28.5 gigahertz center frequency. It is a filter with 7.3% bandwidth, and it has an impressive insertion loss of less than 1.3 dB midband insertion loss. This is a substrate waveguide implementation. We are not limited, or we have not been limited to implementations of filters. We have also experimented with, for instance, not just bandpass filters, but low-pass filters, for instance. And being the LTCC technology naturally a packaging technology itself, we have also experimented with implementation of packages, both on traditional wire bonding schemes and flip chip assemblies. And I have here, for instance, an example of one of these packages, a flip chip assembly of a switch, and some test data that is related to the same. So the academia proved in theory that LTCC can be used to implement circuitry intended to perform up to the millimeter waves. Nevertheless, they're very small production batches, very limited assemblies, and highly customized processes for the fabrication of these or their prototypes. We're still leaving a doubt on the viability of this technology for higher frequency developments. Based upon our investment in both material developments and circuital topologies, we have successfully been able to fabricate millimeter wave components in our production line employing volume and cost scalable processes. Test data, as shown on the above slides, proves that this technology is indeed viable to be employed as a platform to support the most current component needs all the way up to the millimeter waves. And we have test data, as a matter of fact, all the way up to 55, 60 gigahertz. So I appreciate your time, and I hope to be. Well, thank you very much for your time today. I hope this has been illustrative as well as enjoyable, and I hope to keep in touch with you guys, and I'll lead to the question and answer section. Thank you for your attendance.
Thank you very much, Aaron, for that interesting story. It's very interesting how you guys improved the process greatly. Unfortunately, we ran out of time, so if you do have a question, you can enter it into the Q&A box, and we'll try to follow up via email after the presentation today. Thank you today to our sponsors and joining us for this new EDICON online event. Please stay tuned for the next talk on EMC success stories for the Internet of Things beginning after our lunch break. This talk has been recorded and will be available to watch later on. You will find it in the events section of the Microwave Journal and Signal Integrity Journal websites. If you or your colleagues would benefit from this talk, please let them know. And thank you for joining us today.